Okay, welcome to my talk. I'm going to talk about using ensemble sensitivities to estimate the benefit of wind lidars, and this is work that we've done at the University of Vienna together with two colleagues from Cologne and then Takemasa from the data assimilation team in Japan. So the general goal that we were aiming for was that we were trying to estimate the benefit of additional wind lidars for the 1 to 3 hourly wind forecast without running any additional simulations. So no OSSIs, but just all do it offline from already pre-existing simulations. And we have a paper on that. And the way we do it is with what we call ensemble sensitivity analysis or ensemble variance reduction. And the specific method of variation that we use of that requires that we explicitly calculate this linear sensitivity. And on this talk, I want to talk a bit about what we mean by this ensemble sensitivity. There's sometimes a bit of confusion, I think, in the field because people sometimes use the term slightly differently, and then focus on how it can be computed. And then the final part is the point most relevant for us is that how we specifically compute this ensemble sensitivity affect our estimates of the observation benefit. And with that, let's start defining a few things to avoid confusion. So this is all about ensembles. And we here I'll be talking about two ensembles. At a certain time, we have the background ensemble, XB. And from that, we run a forecast, which we call the pre-forecast at time 2. So these are things that we assume we already have from a forecast that's already been run. And what we're looking at is the way we judge the benefit is we look at the variance reduction of a specific forecast metric. So this can be any scalar value that we can compute with response function from the forecast. So for each ensemble, we apply the response function and get one scalar value, and that's our forecast metric. And it could be something like the pressure over a specific area or anything really. And the definition of the ensemble sensitivity that we're using here is that this is assumed linear relationship between the background perturbations in the ensemble background and the ensemble deviation, so the linear relationship between the ensemble deviations of the background and the ensemble deviations of the forecast metric of the free forecast. So this is the link between the background to the forecast, so across time, and we know it's only approximation. And that's sort of what we mean by ensemble sensitivity. So what's commonly done is that you reformulate it using a square matrix, namely here the background covariance matrix. And this is simply achieved by multiplying our approximation here, the original one, with delta xt divided by n minus 1, so that we get the sensitivity times the B matrix is then approximately this vector. So the covariance is between the perturbations of the forecast metric and the background. And just to make things less confusing, I'll just call this second vector A. So we have SB is approximately A. So in theory, if we wanted to calculate S, all we need to do is inverse B and multiply it with A. So why is this not so easy? So the problem is in any meteorological application, B is always going to be rank deficient. So you would need to have more independent ensemble members than your state size to even hope to get your matrix invertible. So the inverse just doesn't exist to begin with. And even if it did, B is most likely going to be highly ill-conditioned. And that means that in this approximation that when you're solving for S for a given A, any kind of slight changes in A could lead to gigantic or will lead to very, very big changes in S. So these are both not ideal. Okay, but just because not possible, people have done it anyway. And the first way that this has been done with, and by far the most common, is that you just get rid of all the covariances. So in the end, you reduce it down to univariate regression. So in equation terms, that means you replace the B matrix, the ensemble covariance, just with the diagonal. And it's been used in various studies here. I think I listed a good part of them for various purposes. And of course, once you diagonalize the matrix, it's trivial to invert it. And the other way is what I'm here calling regularization. It's not been done very often, but there have been 3 previous studies I've found that do it using some form of singular value decomposition. And we use a slightly different one. We use the Tikhonov regularization that's talked about in our 2 papers. So to give a very quick introduction on Tikhonov regularization, one of the most confusing parts of the Tikhonov regularization is that it just has a ton of different names, such as ridge regression, weight decay, L2 regularization, so it can be a bit confusing what people are referring to. But what it essentially does is that it tries to minimize these 2 L2 norms. So the first one, this SB minus A, is our original approximation that we were talking about, where we assume that SB is roughly A. And the second one is alpha S. So alpha is a freely chosen parameter that is larger than 0. And so what it's essentially trying to doing is trying to find a good, like a S that is a good fit for the SB equals A, while at the same time trying to keep the values of S as small as possible. And for any value of alpha chosen, there's a unique analytical solution that I'm showing here. The specific isn't really that important. But just to illustrate it a bit more, so in the case that we would let this alpha value go to infinity, the second of these 2 L2 norms would dominate, and then this the sensitivity would just become a 0 vector. And the other flip side, if you let alpha go to 0, then it becomes equivalent to the pseudo inverse, also known as the Moore-Penrose inverse. So to show what the sensitivity actually looks like, I'm going to be applying it to a linear advection toy model that we use, and I've shown it here for 15, so just one test case with 15 ensembles. And it's so the toy model has a 300 state vector size of 300, one variable here phi that ranges roughly between 0 and 1, and shown here is sort of the lead time 0, so that's our background ensemble, and then 2 different forecast lead time. And all that happens in this linear advection toy model is that each of the ensemble moves to the right with a slightly different speed. So in general, there's a sort of clear mean ensemble propagation, but the individual ensembles move slightly differently. And the forecast metric that we'll be using here is just the sum over the middle of the main. So this is what I call this sum here from 100 to 200 that's shaded in gray. And that will be our cost function that we'll be looking at. And importantly, so the reason I showed 2 lead times instead of just 1, that as the lead time goes bigger, the ensembles start spreading more, and this basic assumption that there is a linear relationship between the ensemble deviations of the background and the forecast becomes less and less accurate. And as we'll see, that's important. So I showed this, I only showed 15 ensemble members just to make the plot a bit easier to see. Here I'll be using 60 ensemble members when I actually calculate the sensitivity, here shown for 3 different alpha values, so with more or less strong regularization. So here on the y-axis we have the delta j to delta xi, so how the sensitivity of our forecast metric to each of the state components. And in here is this dashed line, and the dashed line is important. So for a lead time of 0, we can directly analytically compute what the sensitivity should be, because it's we know it's just a sum. So in the middle of the domain, it's a 1, and outside of the middle of the domain, it's a 0. So the sensitivity we compute should ideally just be this dashed line. And then with increasing lead time, we don't know exactly what it should look like, but we know that it should be moving sort of upstream with the mean advection speed of the ensemble that you saw on the last slide. So we have a pretty good idea what our sensitivity should look like. And now shown in these 3 red lines are the sensitivity we computed using the Tikhonov regularization. And if we look at the 0 second lead time and the low regularization, we can see it's doing quite well. And then as you go to longer lead times and this linear sensitivity assumption starts to break down, you can see that things get noisier and noisier, and you have to use and you do need more and more regularization, sort of damp these oscillations that occur. But in general, things have sort of the right magnitude. especially with 300 seconds, you can see they do clearly identify what the sensitive region should be. So it works more or less with ensemble problems. And now I want to compare this with what you get if you use this univariate sensitivity that's often used, again with 60 ensemble members. And I use the same dashed line, it just looks straight because the magnitude that we get when you use this univariate regression is much, much higher. So here we're going from minus 100 to 100 instead of the 0 to 1 that we'd hoped for. And you could argue that with this univariate regression, you don't expect it necessarily to be quantitatively correct. But what I find quite, not worrying, but it's good to keep in mind is that qualitatively it's also very difficult to understand. So here we have a clear region that is the middle that should be the most sensitive, and you don't really see that. And also, if you looked at the time evolution, it looks like there's no sensitivity at 300 seconds and then more at 600 seconds. So I'd just say to this is be wary if you use this univariate regression. So now I talked about the toy model stuff, and to briefly get to the results. So when we were looking at wind lidars, we were using NWP forecasts with a 1,000-member ensemble. Details of that in this paper by Necker 2020. And there we had a reduced state size of roughly 5,000 and 1,000 ensembles. And shown here is a selection of the sensitivity for 0 lead hours and 3 on the right. Each of these dots is one of the reduced grid points, and here the coloring is the sensitivity. And this green square marks the domain where we calculated our response function over. And the important part here is that the results we get are actually quite similar to what we got with the toy model. They sort of fit what we theoretically would expect to see. There's sort of a bit of ensemble waviness, let's call it. And as time, so if you go to longer lead times, in general, the sensitivity decreases, becomes a bit noisier, but that's exactly what we would expect to happen. And the specific pattern here also matches the synoptic situations of that specific day.
2-minute warning.
Okay, thanks. I got 2 slides left. So, and this is sort of the important takeaway slide from this talk. So shown here is the relative variance change, which is what we use as our metric to guess the benefit of adding these wind lidars for 3 different lead times. And on the y-axis, that was on the y-axis, and on the x-axis, we have different values of alpha from the regularization ranging from 10 minus 5 to 10 to the power 4. And you see if you apply very high regularization, like 10 to the power 4, you just completely flatten any sensitivity and you end up with everything being 0, which we don't want to happen. But what's good for us is that there's actually a wide range of values of alpha, basically over 5 orders of magnitude, where the benefit we estimate is independent of the specific value. And that's good for us because that means that if we choose any of the values in there, we're probably going to get a pretty reliable estimate that won't change dramatically just by tweaking that alpha tuning knob. And it also fits, yes, so we would expect that the longer the lead time, the less benefit we get from our observations. So everything sort of matches how we think it should behave. So to get to my summary, first point is if you do use this univariate ensemble sensitivity, beware. I think it's a bit harder to interpret than some people assume. The second point is that for this way that we estimated the benefits of these additional wind lidars, we're quite confident that it's not very sensitive to the precise Tikhonov value that we employed. So we're quite happy about that. You're free to ask questions, of course. I'll gladly answer them. Otherwise, we have 2 papers on this currently, both under review in the quarterly journal, and the one by Tatiana Nomokonova should come out hopefully pretty soon, talking about the lidar estimates. And then there's a paper of mine as well that's hopefully going to be around sometime that really talks about the specifics of the method. And that's it. Thanks for listening.
Thank you very much, Philipp, for this great talk. Very interesting. And I already see one question by Hristo in the Yopad, and he asks, how do you interpret the fact that the optimal alpha value in the Tikhonov regularization increases with lead time? Is there a way to choose alpha adaptively?
So first of all, yes, there are ways to choose alpha adaptively. I'm sure there's books written about how you can do this. We sort of stuck with the constant one for now because it's simple. And the explanation is that our B values, so our B matrices are very poorly conditioned. And that means that sort of any deviations in our, if you remember, it was S times B equals A. So any deviations in A start leading to bigger deviations in S. And our A is a covariance, so it has ensemble noise in there. And as time goes on and this sort of approximation breaks down, you get more and more deviations from sort of what it would look like if it were equal. And this then means that you get more and more noise on S, and that's why you need to apply stronger regularization for longer lead times, or just general. The more non-linear, the worse the sensitivity, the linear sensitivity approximation holds, the more regularization you need to apply to get it to work anyway.
Okay, thank you. So let me check the Yopad if there's another question coming in. That's not the case. I would say, in the interest of time, we move on. Thank you, Philipp, very much for the talk.